to demonstrate the pros and cons of the methods, let me talk about this very quickly. So why is CUR method good? First, CUR method is very easy to interpret, right? Because the singular values and singular vectors, right? So the rows and columns of C and R are simply the actual data points, right? They're actually rows and columns of our data matrix. So it's very easy to interpret them because it's actual data. Another good point is that our axis vectors, right? So again, vectors in C and R, so columns in C, rows in R, they are actual data points. So if the original data is sparse, these vectors are also sparse. One drawback, though, is that we have duplicate rows and columns, in a sense that rows that are very long will be sampled multiple times. But this last drawback is very easy to get around, and I'll show you an example of how we can do it, right? So in some sense, what is the difference between the two? The difference is that if we have a set of data points in a cloud like this, a singular vector will be kind of the best point to project, but what a CUR vector will be, will be some actual data points, so it will be a bit off, but everything will still work. So this is what we see from the CUR decomposition. Right, now the question is, how do we get rid of the duplicates? Right? So the idea is very simple, right? The idea is kind of, let's throw them away, but then let's scale, in some sense, multiply the original row and column by the square root of the number of times it appeared in our original data, right? So if I have matrix A, I compute my CUR decomposition. Imagine that I have a certain column here sampled multiple times. Then I would only keep one copy of that column, but I would have to multiply it with the square root of D, where the D is the number of times that column actually appeared in my data. And I would do the same with R, and I would then construct the matrix U the same way as we talked about. So everything still works, everything is great. So how do CUR and SVD compare to each other? So in both cases, we assumed that matrix A is our given input data matrix, which is very big, and let's think of it as sparse, so it has lots of non-zeros in it. And then the way we thought about SVD was that we have matrices U and V. They are big but dense, and matrix sigma is sparse and very small. Okay? What is CUR? CUR also has A that is huge but sparse, but what is now important is that C and R are also big but sparse, and now matrix U is dense but small. So the difference is in SVD, sigma is sparse but small. In CUR, our kind of corresponding matrix U is dense, but it's still very small, so kind of it doesn't matter. But the big difference is that C and R are sparse, while in SVD they are dense. And just to give you an idea how much this makes a difference in practice, let me tell you about a simple experiment. Okay, so what we will do is we will take the DBLP dataset. So DBLP is a biographies of all the computer scientists, right? So for every computer scientist, there is a set of papers they published. So what we can do is, for example, we can create this matrix of author to conference matrix. We can think of it as a big, thin matrix where columns are different conferences and every row is a different user, right? So this is a different scientist and every column is a different conference. And then the entry simply tells me how many papers did a given author or a given scientist publish at a given conference. So in terms of this matrix, we have around 400,000 authors, 400,000 computer scientists, and we have around 3,500 different columns. Okay? And this matrix is very sparse, which means that most computer scientists don't publish at most conferences, right? Out of these 3,000 conferences, most computer scientists maybe publish at 5 or 10 or of them, and the rest they will never publish at, right? So what do we want to do now is we want to reduce the dimensionality of this data, right? So what do we want to what are the things we want to understand when we do this dimensionality reduction? We want to understand how much time does it take to do the dimensionality reduction, what is the reconstruction error, and how much space do we need to store the new data points and the new dimension, the new basis vectors, and so on. So let's look at the experiment. So this is done from the paper by Sun and Faloutsas from 2007, and here are the two graphs, right? So the first one is the accuracy. The accuracy simply means what is the reconstruction error, right? So 1 means there is no reconstruction error, and 0 means we have lots of reconstruction error. right? Blue is SVD, and the black and the red are CUR, CUR with duplicates, CUR without duplicates, and the y-axis here is the space ratio. How much space do we need to store the basis vectors and so on? And what you see, for example, in this case, because our data is very sparse, is that to achieve the same accuracy, let's say to achieve accuracy of 0.2, CUR needs much less storage than what SVD needs. So in some sense, SVD needs less vectors, but these vectors are dense, so we need to store every possible coordinate of them, while CUR eigenvectors or singular vectors, if you think of them this way, are sparse, and we only need to store the non-zero ones, right? So for the same accuracy, we need much less storage for CUR. And of course, if you also think about the computational time, here is the computational time that we need to achieve a given accuracy using SVD versus computational time to achieve given accuracy given CUR. And again, what we see is that for a fixed accuracy, CUR is much faster than SVD. Of course, what is important here is that in most cases, the number of actual vectors or the dimensionality of the reduced space to which we are projecting in SVD will be smaller than in CUR, but the amount of space and computation will be much better in CUR. So with this, we are done with discussing the topic of dimensionality reduction and the application where we will really need all these techniques in terms of the singular value decomposition and thinking about matrices and representing them in low dimensional space, and in terms of the concepts that appear in these matrices will be in terms of recommender systems, where we will be given a big rating matrix of users to movies, and we will want to identify, basically exploit the correlations the same way as we were doing in our movies to users example, in order to identify which movies to recommend to which user. So this is what we will look at in a couple of next lectures.